recording on this computer. And what we're talking about is Bragg scattering. And it looks a whole lot like the interference and diffraction gratings that you did in PHY112 and that we did at the start of this semester when we were talking about optics. That problem is still important. It's just different from what we're talking about now, which is Bragg's work with X-rays. And instead of running X-rays through like a glass piece of slide with a bunch of lines etched on it, like we do with a diffraction grating, Bragg used crystals in materials, metals, things like that. Okay, so let me start sharing my first my PowerPoint with you. And where's the share button? It moved it off there. All right, yep, looks like you're seeing it. And so just a couple of things that are different about Bragg scattering, and we'll go slideshow mode here. Bragg scattering compared to other diffraction experiments, things like that. And the first most important thing is anytime we did an optics problem in PHY112 or whatever physics class you did before, the angle, if there's the edge of the object right there, we always looked at a normal, and then the angle would have been that angle right there, okay, theta. In Bragg scattering, we don't look at the angle with respect to the normal to the surface, that the incident electromagnetic radiation in the case of Bragg X-ray, but if the prism, it's visible light, and we talk about Snell's law. If it's a diffraction grating, we always look at that angle, okay? In this case, we're looking at the angle theta. So let's change this. I don't want that to be theta. Let's, where's my little annotate tool here? I want to erase that, I guess. I don't want it to be theta. Let's instead change it to be a different angle. Call it phi. And we'll talk about that in a bit. And we're going to show another equation for Wednesday where we will look at the angle with respect to the normal as opposed to the angle with respect to the surface, as in the case of Bragg. Just pay attention to which you're given in a problem statement. Are you given theta with respect to the surface? Or are you given phi with respect to the normal? Okay. The next thing, I guess, is that if we were looking at Young's experiment or diffraction grating, we would have said that some integer multiple of wavelengths, and I used M in the pre-lecture video, and I truthfully don't even remember what we used in PHY 112. It could be an M, it could be N. All that means is an integer. And, whether we use an N or an M, if that bothers you, you got to get over that. Okay. But the point was that integer multiple of wavelengths, if it was D times the sine of theta, well, that was constructive interference. And in Young's experiment, real quick, the reason for that is if some light was coming from these two openings out to some angle right here, we think that bottom aperture, the light coming from it, has to go some extra distance, D times the sine of theta. Okay, and this is an approximate because those two lines aren't parallel. So this can't be an exact right angle, but the angle theta is right there, or the angle theta is right there. Okay, and so D sine of theta is the extra distance the light coming from the bottom source travels. If that's an integer multiple wavelengths, we say we got constructive interference and we get a bright spot. Okay, that's not the way it works for Bragg. And oh yeah, by the way, that angle theta is with respect to the normal, to the plane which contains the two openings, the two slits, the two apertures, whatever you want to call them. In Bragg scattering, instead, we're doing kind of a reflection process. So I guess I'm going to add that as a third difference, as opposed to going through the plane out to some screen in a normal diffraction or interference experiment. And you notice that there's a little extra distance right here, exactly like this D sine of theta, but since it's a reflection, it occurs twice. And so what we say in Bragg scattering is the light that reflects off the second plane of atoms as compared to the light which reflects off the first plane of atoms, and I'm saying light, any electromagnetic radiation. In the case of Bragg, it's X-rays, and all we need is a plane wave right here. And all that means is parallel wave fronts coming in here, moving that way. Okay, the bottom plane, the next plane down, travels an extra 2 times d sine of theta. Okay, and so that means the constructive interference case now is not n lambda or m lambda, whatever you want. And in our book, we're using n this year for Bragg scattering. If that extra distance is an integer multiple of wavelengths, I'll get constructive interference. But now the extra distance is 2 times d times the sine of theta, right? And so I, just want to point that out. This is obviously a very valid physics equation up here for diffraction gratings or Young's two-slit interference. That's not Bragg's equation. Differs by a factor of 2, and it differs by the way we define the angle. And if you can live with that for Bragg scattering, we're good to go. All right, now I do want to, because I think I'll have time, the two problems, the problems that we're going to do today on our worksheets are slightly simplistic. How's that? All you're doing is you're identifying and using that simple equation. Fairly straightforward problems. I do want to jump ahead to something we're going to talk about on Wednesday, because I think I have a moment to do so. So let me stop this. Yeah, no, discard my annotations here. And I'm going to stop sharing that PowerPoint. And I'm hopefully going to go to the de Broglie PowerPoint. And so I'm going to share that with you real briefly. We'll talk more about de Broglie and all these other folks. Is that the one I want? Yeah. Okay, we'll share that. And just because you find that so often in science that people can't agree on a convention. Are we going to define the angle with respect to the surface that we're reflecting off? Are we going to define it with respect to the normal? And the point, I guess, I need a pen here. I'm searching around for it. There we go. My obnoxious red. Put that away to make that a little bigger. And here's what we just talked about for Bragg scattering. Okay, and lambda is equal to 2d sine of theta. And angle theta with respect to the normal, I'm sorry, with respect to the surface, there's the extra distance that light that reflects off the second layer of atoms travels compared to the first. If that's an integer multiple wavelengths, constructive interference, we'll get a bright spot. Okay. Some guys named Davidson and Germer, they're going to do a different experiment here. And let me make this bigger so that you can see it by going to that. And our textbook decides to talk about an angle alpha as the angle with respect to the normal now. And they bring the incident beam of X-rays in this way, and we'll talk more on Wednesday about what they actually had hit an array of atoms in a crystal lattice. They bring it in, and it looks like it's normal to that, what we'll call the principal plane, the ones that are horizontal as I'm drawing this right here. And of course, if that was the plane that you're reflecting off, it would just bounce straight back. Okay, so we're going to look at a different plane, the ones with the dashed lines, and you can see there's the normal to that plane, that blue line right there. And our textbook talks about alpha. Alpha is nothing more than this total deflection angle phi divided by 2. Okay, and so I think I called that phi on the Bragg diagram. The incident angle with respect to the normal is really half of phi. All right, so that's the first thing that you gotta work with. And this is the two scientists, Davidson and Germer. They do a similar experiment, only they can't follow Bragg's convention for theta and wavelength. Instead, they use this different one. Okay, and let's see. One of the first things that you'll notice is, I guess, if I was to take the sine of the angle theta that would have to be equal to the cosine of that angle theta over 2. And I'm hoping that's obvious because those two angles, theta and phi over 2, they're complementary. They add up to be 90 degrees. And so essentially what we're saying here is that the sine of an angle, I got to get my pen here, the sine of any angle is equal to the cosine of 90 degrees minus that angle, right? And, if you got a 30-degree angle, the sine of 30 degrees is 1/2, and the cosine of 60 degrees is 1/2 because of that rule. If these two angles add up to be 90 degrees, the sine of one is equal to the cosine of 90 minus that angle. Okay, and so we've got that exactly going on here. So the sine of that angle with respect to the surface is equal to the cosine of the angle with respect to the normal, which we're calling theta over 2, because we decided that the total deflection will be phi. Could have done this differently, but that's just the way our book chose to do it. All right, now let's look at this plane that's not the principal plane. And by principal plane, I would mean these guys right here, okay? The kind of edges of a cube, the ones that cut across some diagonal of, in this case, multiple cubes. If I want to figure out the distance between these dashed planes that were already drawn in black, well, I think this angle, either alpha, which is actually the same as phi over 2, the incident and the exiting angle, show up right there. And so I've scratched out alpha and I've written phi over 2. And so the separation between planes, the particular planes we're scattering off of in this experiment, is the principal distance, which is labeled, it could be right here if this is a cube. You can see it's labeled right here. Assuming it's cubic, those are exactly the same dimensions. It would just be this side d would be d times the sine of phi over 2. All right. Bottom line, I think, is it's still Bragg scattering. So I still believe this is true. I just got to, for Davidson and Germer's experiment, which we'll talk more about on Wednesday, they redid the process just to make it confusing for us. They decided not to use this angle. They decided to use this angle divided by 2. All right, well, let's take care of that. First thing is let's substitute in for D right here, what we just decided. And then let's use this rule about the relationship between sines and cosines that are complementary and plug that right in there. And so we still got the n lambda, constructive interference, still integer multiples of a wavelength cause things to interfere constructively. But what do we have? I got this guy, I got this guy, and I got that guy, and that's a trig identity. It's called a half angle formula. 2 times sine of phi over 2 times cosine of phi over 2 happens to be d times the sine of phi. Now, I just, it looks nice. It is still describing the Bragg scattering phenomena, right? Like some incident beam comes in, some scattered beam goes out, okay? It's just, it still has constructive interference, but this one is using the angle theta, which is defined right here. This experiment is using the angle phi, which is the total deflection angle. I personally would have used phi over 2 myself, just to have the angle with respect to the normal. And it's using capital D, which is that dimension between the sides of the cube, okay, as opposed to what Bragg uses, which is the actual distance in between the planes, which in this diagram is exactly the same. But if you're ever doing Bragg scattering off of a different set of planes, like maybe this one, well, you would have to figure that out using exactly the same relationship I just did for the Davidson-Germer experiment on the right. And so I only point that out because in the same chapter, in 2 adjacent sections, you're seeing the same phenomena, what we're going to do today, Bragg scattering, and what we're going to talk about on Wednesday, which is the Davidson-Germer experiment. They're essentially the same thing, but yet defined with respect to different variables. And if you're wondering why the difference, well, we just went through them. All right. Any questions on that? I'm going to stop sharing this, and then we're going to go on. I don't have any It's trying to stop sharing it anyway. Put that away. Don't want to keep my annotations. All right, we got everybody's here now. Any questions on that? All right, so let's go over to the worksheet for today. And I'm going to do one problem, and then I've got 3 more to do. And again, it's Young's experiment, diffraction gratings, as compared to Bragg scattering, which is what we're going to be doing today, as compared to the Davidson-Germer experiment, which we're going to talk about on Wednesday. Make sure you get the right equation. Today's the one we're going to talk about. N lambda is equal to 2 times d times the sine of theta, where d is the separation between the planes that the Bragg scattering is occurring from. Okay, so I'm going to go over to my my iPad here in Notability, which I got queued up. Come on, share. Now I got to do screen mirroring. It's working good. And hopefully, looks like, yep, you're seeing it. Now, I do want to point out, if you've already downloaded the PDF document for today, you can see that as I went from Canvas to Notability, I lost some detail here in my diagram. And so if you go back to the original original PDF, you'll notice that there was, come on, pen, turn on, stylus, work. All right, there was something that looks like that. And then there was an angle right here, theta, that was labeled, and then light was coming in right here. And so if you've already opened it, hopefully yours did a better job of finding finding all the attributes of the diagram that I so carefully put into this worksheet. Okay, it's labeled problem 0 because it's the one I'm doing, and it is the review problem from earlier in the semester and even last semester. I don't even know if I've changed the numbers. We're given 2 narrow slits, 0.2 millimeters apart. And so this distance right here, I've drawn my lines right where I want them. That distance right there is 0.2 millimeters, right? And the screen that we're letting these 2 slits form an image on is out at 1 meter away. And let's see, it says, find the angular position for the m equals 2 bright spot on one side of the center fringe. Okay, and truth, I don't care if you find the answer in radians or degrees. I got both here, but pretty straightforward problem. In this case, m times lambda is equal to d times the sine of theta. Not exactly Bragg scattering. That's why I'm doing it, so you don't do this. Okay, and now what other things do we know? I don't think I circled the other piece of information I need from there. What's the wavelength of the light, the electromagnetic radiation? And oh yeah, m equals 2. I did circle that. So in this problem, literally, it's the easiest one I can think of to do. That's why I'm doing it. 2, 633 nanometers. And what am I trying to find? D, oh, I didn't circle that either. 0.2 millimeters, and then times the sine of theta. Okay. Now I could cancel the meters. The problem is I have a nana and I have a milli on opposite sides of the equation, don't I? But if I continue to solve for this, angle, sine of theta, is going to be equal to 2. Why did it do that? I thought I needed to do that, I guess. 2 times 633 times 10 to the minus 9th. I've already canceled the meters, divided by 0.2 times 10 to the minus 3rd. And when I did that, I got 6.33 times 10 to the minus 3rd. And then I just converted that's radians, right? Because the sine of the angle is approximately equal to the angle when it's a small enough angle, and that certainly is. So you could take the inverse sine in radians if you want. If you don't believe me, do it. You'll get exactly the same number. When I converted that to degrees, I got 363, oddly enough, as my angle in degrees. Okay. Young's interference, this would be the same way I would go about a diffraction grading problem. It's not going to be the way you do the three problems that we're going to do here in class for Bragg scattering. I do it to point out, don't do this. Your equation will be slightly different. Your equation is still some integer multiple of wavelengths, gives you constructive interference, gives you a bright spot. But because you're reflecting off of Bragg planes, 2 times d times the sine of theta will be the equation you're using. And remember, your angle is with respect to the surface. When I did Young's interference, the angle I was given there that I was calculating was the angle that the deflection occurs with respect to the normal to get to that bright spot. Okay, so 22 degrees here. Reflection peak centered at 22 degrees. What's the Bragg spacing? Well, I'll let you guys work that out. Okay. But I think you can assume that is the right angle that's given. A couple of people will go the other way. This one has you figure out what the wavelength is. Nope, I'm sorry. What's the plane spacing? So you're solving for D in the first problem. And then group 2 here, we'll divide you up in a second. Looking for the angles that the second and third order peaks will occur. Okay. And then in this one, the third group, you're looking for the wavelength. So each of the 3 problems is slightly different in what you're looking for, but in each case, you're doing it the exact same way. Any questions? All right. So I'm going to stop sharing this and I'm going to break us up into 3 groups and we'll see let's see, where's the groups? Breakout rooms. There we go. We want 3 groups. And the computer randomly selected Anaya, Prince, Sam. You guys are doing problem 1. Problem 2 is Justin, Max, and Saeed. And problem 3, working by themselves, Amaya and Shniha. You got the third problem. And they are numbered 1, 2, and 3 because the problem I did, I labeled 0. Any questions about any of that? All right, we'll have fun for a few minutes and we'll come back and show each other our solutions.
Ask him. Then I was like, I'm not going to get one. And then I got one. Oh, there he is.
Hey, one thing I'd ask, do draw the picture. I mean, it can be pretty crude. Just draw the boundary, draw the angle, just so that the equation gets linked up with a picture for yourselves.
Okay. Also, is n equals 1 for this one?
Scatters from an unknown sample and a Bragg. You know, that is the only assumption that I think you can make, right?
Right.
It
Yeah.
doesn't
Okay.
say. And so because it's a fairly small angle, my answer is going to be yes. If you're not told otherwise, assume it's the first order reflection.
Okay.
Yeah, your picture's getting way better than I was expecting, but this is good. Exactly what you're doing great, more than I was even thinking. So I'll leave you guys alone. It looks like you're on the road. Not a really hard day today, is it? These
No.
aren't the most complicated problems in the world. As long as you keep things straight, what the angles are, what the distance d is being referred to is, the math is pretty straightforward. Yeah, and that's exactly the only thing you might. Yeah, there you go. That dash line. Now you got everything I was looking for. All right, I'll leave you guys.
So we're kind of looking at
I would not use my picture because you're doing Bragg scattering. I was doing the one that you don't want to confuse with Bragg scattering.
Really?
Yeah, so
Oh,
you
damn.
draw, and
Okay.
that's the first thing I would ask you to do. Draw a different picture because this
Okay.
picture isn't the right one. The picture you want is the one that I was working with earlier. Yeah, I don't know. Do you have that? Hey, you do, don't you? It's
Let me look it up.
yeah. Pull up the PowerPoint I was doing. I gave it's in a PDF in Canvas.
Okay.
Can you do side by side? Yeah, there you go.
I got some
Okay, keep going,
screenshots.
keep going, keep going. There, that one right there. That's your picture.
This one. Yeah.
Yeah.
Ah,
See how it's different, right? And that's the point. It's a different picture.
gotcha. Okay. Uh, okay. First order. We have the first order.
Yep.
And we're asked to find the second and third. But the equations are the same. They
A
it's just
factor of two, though. Yeah.
yeah. It's yeah. The basic one is d sine, right?
That would be true for Young's experiment diffraction grading. For Bragg scattering, you got that
Yeah.
2d sine of
d
theta.
sine theta. Correct. Good.
And that's the difference. And the angle is with respect to the surface, not with respect to the normal. Okay. All right, I
This
think you're
one.
off. And you got to calculate two angles now, right? One for m equals 2 and one for m equals 3. And you're good to go.
Yep, that sounds right. Yeah.
Hold it. I lied to you. What are you
What?
trying to find? She's got to,
You said you're supposed to find the angle to the surface, not to the
yes,
normal.
yep. But
So
the problem here is you don't know what D is, do you?
no.
So you got to get
We
D first
we
from the
don't, yeah.
fact that the first order is at 12.5. And then
Yeah.
once you got D, then you got to solve for the angles for 2 and 3.
You are correct.
Yeah. Right. And there might be a different way that you can manipulate the problem, but that is what you have to go through. All right.
Cool.
All right. I'll leave you guys. You're on your own now. All right. 2 times that, 30. Why'd you go 31.6?
Because twice the angle that's given.
Yeah. Okay. So now I'm going to ask you to draw a picture then. Yeah, that's what I was worried about is you went with the Davidson-Germer experiment. Let me share my screen with you. I'm going to probably overwrite yours for just a second. So let me hold on that. And hopefully you're seeing my PowerPoint. The angle that you're given in that problem statement, I think is this right here. Okay, so you don't have to double it. You would double it on Wednesday when we do a different problem, but for today, just use the angle with the way I read that. If the first order Bragg reflection is observed from a principal plane at 15.8 degrees, so there's the principal plane, and this angle, I think are 15.8. So I don't think you need to double it in this picture, okay? Did I convince you?
Yeah.
All right, yeah. On Wednesday, when we use that angle phi, you will be doubling it, and it'll be with respect to the normal. But I think in this particular case, in Bragg's reflection, the angle is with respect to the surface, with respect to the principal plane, and it's not doubled. All right. So here's what I do want though, and this is kind of the point. Draw a picture with your solution as well, just so you define all the angles. All right, I'll stop sharing so you can go back to what you guys were doing. Any questions?
No.
Then I'm going to leave. I'm back. And I agree with you there. Okay. Sounds good. I'll be calling everybody back here in just a minute. Perfect. Good diagram. Gets the message across. See you in a little bit.
He said his name is Mr. Gibbs. That's so cute.
Oh, we're showing puppies now. Cool. You guys are done? What number did you get?
Got 133 picometers.
133 picometers. I got to think. I'm worried about the power of 10. I got 1.33 times 10 to the minus 10th. And so
Yeah.
you're in picometers. So wouldn't that be 13.3 picometers?
Is in picometers to the
Oh, no, I'm
minus
sorry. You're
12?
right. You're right. 10 to minus 12. So it would be 133. Yes, indeed. Absolutely. Yeah, what kind of dog is that?
He can't really speak, but he's saying it's a husky mix.
Okay, gotcha. All right, I have a black lab. If we'd have known how great labs were, we'd have always had a lab. They're awesome dogs, but I'm sure that's good too. All right, you guys are done. I'm going to leave and make sure the middle group is done. I'll be back and we'll call everybody back to the class.
Got it.
All right. Leave breakout room.
Oh, Justin, you need to sleep, man.
All right. I agree with those numbers. So let's end the breakout rooms and get back to class.
Awesome. Sweet.
All right. 1, 2, 3, 4. We're coming back. All right. Gonna mute yourselves. All right. So hopefully you're seeing my my screen here from Notability, and pretty easy problem for today. I think you'd have to admit, but as people who study physics and have taken now, you're in your first upper level course in that, if you were to look at an equation sheet, you'd see all these equations for interference and diffraction phenomena, superposition to get constructive interference or destructive interference. And depending on the geometry, the first one here, that's interference. It's also diffraction gratings, right? But there's a picture that goes along with that equation, and keeping it straight is the hard part. I didn't talk at all about that second equation here. Anybody recognize what that is? So the first one was like two slit interference, right? Or a diffraction grating. You would use that first equation. What's that second one for? What is A here? Yeah, the 70 that I had for PHY111, you're making me feel bad, but that's all right. My 101 students do that. That's a single slit, isn't it? So if you had just a single aperture and something like that, and it was to make a diffraction effect, and it actually has other bumps on either side, that gives you the angle at which not the maximums occur, but oddly the minimums, where those 0 points are in a single slit diffraction pattern. Okay, that's a pretty poor rendering right there. So I'm going to try that again, just so you get the point. There's that central hump, and then there's these little guys off on the side. Okay, that's what we're calculating, and we're finding the angle of the minimum right there. Go back and look at your night book if you've forgotten that one. Of course, this is the guy we're doing today, Bragg. Okay, this is the one we're going to do on Wednesday, Davidson Germer. We're all doing the same interference phenomena, but we're just using different geometries and different pictures. And that's why I think for each group as I came through, I said, please draw a picture. Okay, I might not have even said please because sometimes I'm not polite, but that is the point. All right, so I guess the first group, if you guys want to just show yours wasn't too bad a problem. Who was it? Was it Prince was in that group? I've forgotten already because I'm Sam. Okay, Sam, you've got it. Pulling it up.
Yeah. So we made the assumption that n was 1 because the angle was so tiny.
Yeah.
And they gave us no other information to assume it wasn't 1. And then we literally just plugged everything in. So they gave us the wavelength, we plugged that in. And they gave us the angle and we plugged that in, and we solved for the D because that would be the spacing. We got 132 picometer.
Okay. And the other thing it didn't tell you specifically is how that angle was defined. but since the problem statement said this is Bragg reflection, you can assume that angle theta is defined the way we discussed. And that as you go from textbook to textbook or website to website, physicists have accepted for Bragg's interference, the angles are as drawn in your picture here. Okay. Questions on that one? Pretty straightforward. I think group 2, you guys had the hardest problem, I think, see, because yours was multiple steps. So and then they had to calculate 2 angles. So go ahead and show yours if you would. All right, bringing it up.
Bring it up, yeah.
There you go. Yeah, sometimes you draw the hardest problem and not difficult necessarily, but you just had more steps to do than all the other problems.
Someone want to explain, or should I go? All right, I'll go with it. So we basically had to find we were given the Bragg's diffraction peak of, angle 12.5 for the first order. And we were asked to find the second and third peaks. But then we also didn't have the wavelength, we didn't have the distance. So we had to kind of use a system of equations to plug in lambda, which we know what this is. Once we did that, the D's kind of canceled out, and we solved for both the other angles, and we just changed the M's.
Yeah, see why theirs is harder. They didn't know wavelength, they didn't know D, so they basically had to find the ratio of those two and then plug that in, okay? And so if you look where it says n lambda right here, they put in 4 times D times the sine of 12 and worked it out. And it does turn out to be double, doesn't it? I guess, yeah. I did it slightly different. Your reliance, now you got the right numbers, so I'm gonna go with you. Okay, 27.5 and 40.5 were the next 2 up. There you go again. I guess sine of 12.5 I found to be 0.216. So that was helpful. And then you had to take an inverse sine, I guess, to get that angle. See where they had an extra step? It wasn't extremely difficult, but just a little harder than the first problem, certainly. And I think the third problem, if you guys want to go on. Oh, and because theirs was a little more difficult, I didn't make them redraw a picture, but we did refer to the picture in the PowerPoint, and you always want to keep that in your mind when you're applying the equation. Okay, next group.
So we were given the lattice spacing, which was 0.282 nanometer, and then we were given it was the first order, so n was equal to 1, and we were given the angle which observed from the principal plane, which was this, and then we plugged it in to find the wavelength.
Yeah. And the one thing I'll tell you that they were thinking about was, do you double that angle or not? And that we will on Wednesday, not when you're doing Bragg scattering, right? And so that's why this picture right here with the 15.8 degrees defined right there with respect to that dash line, that's the right answer. And keep that straight in your mind. Keep these equations straight in your mind. On Wednesday, we'll be defining the angle slightly different, and we'll have to just adjust. And then when you do a WebAssign problem for next week, make sure you know which experiment we're doing and how the angles are defined, because if you're getting the problem wrong, that's likely the problem. You've done something, you're assuming the wrong angle, something like that. All right, looks like we're just about finishing up. I'm 3 minutes early today. Pretty straightforward material. More to talk about on Wednesday. Any questions? Well, then you just have a great day. I'm jealous of the group with the puppies. That was well, they were done a second early, and so they had a moment or two to look at good-looking dog pictures. I'm going to go pet my dog right now, too. Have a great afternoon, and we'll see you Wednesday. Questions? All right, see you then.
Thank you.